Hello and welcome back to our plasma physics course. Today is lecture 20, and we're going to pick up from where we left in the previous lecture. We're going to finish talking about waves in unmagnetized plasma, and we'll start talking about what happens when there is a magnetic field. If you remember, where we left was with the discussion. Let's see if I can make this happen, of the transverse mode and the longitudinal mode that can occur in a plasma without a magnetic field, where transverse means that there is no electric field in the direction of propagation of the wave. That means that K dot E is equal to 0, while in the longitudinal case, there is no component perpendicular to the component of the electric field, perpendicular to the direction of propagation of the wave, and that means that K cross E is going to be equal to 0. And of course, here K cross E is not 0, and K dot here is not 0. Otherwise, if they were both 0, the vector would be 0. We wouldn't have the electric field would be 0, and we wouldn't have a wave. We're going to follow again our textbook here with some minimal variations. We're going to start from the transverse mode. Okay, well, in general, remember K is KZ Z hat. That is, K is in the Z direction. Therefore, looking up at our definition with the, or refresher, what the transverse mode looks like, we see that the electric field for the transverse mode needs to be Ex and Ey and 0. And I hope you remember that we had been working in Fourier space, and that's what we're going to keep doing. Remember, the Fourier transform is a linear operator, and it acts independently on each component of the field. That means that if the Z or Y or whatever component of, let's say, the electric field is 0 in Fourier space, it's also 0 in physical space, and vice versa. So I wrote here X and Y component non-zero and Z component equal 0 for the electric field in physical space, but I could have done the same thing for Fourier space, and one imply the other. Now, you see that hopefully you see that the magnetic field in this case is not zero. Well, let me type it. The reason why we see that is from Maxwell equation. Remember that del cross A, where A is any vector in Fourier space, turns into IK cross A Fourier transform. But dB over dt is the curl of B I wrote it backwards with respect to how we normally write it, but it doesn't matter. So if I put this in Fourier space, that's going to give me that minus I omega B Fourier transform is equal to minus IK cross E Fourier transform, and therefore that B in Fourier space and the E and minus signs cancel out is equal to 1 over omega K cross E. So clearly there is a magnetic field in the transverse mode. Remember, we started saying that the plasma was unmagnetized, and I tried to emphasize that what that meant was that there was no equilibrium magnetic field. However, as we've just convinced ourselves of, there can be a magnetic field in that is part of the wave. This is an electromagnetic wave where magnetic field corresponds to the presence of an electric field. Of course, you see that since B is K cross C and K is in the Z direction, if I take the electric field to be in the X direction, the magnetic field will be in the Y direction, and the three fields are perpendicular. If the electric field is in the Y direction, then the magnetic field will be in the X direction. And again, the three fields are perpendicular. Okay, let's see what else we can find out about this wave after a technical pause. Okay, here we are. As you will probably notice, I've put my iPad back into light mode because the dark side, the dark mode was just not working tonight. Okay, back to our transverse mode. You will remember, since we just said it a few minutes ago, that K dot E is 0 in this case. Well, k dot the Fourier transform is 0, rather, that means that divergence of E is equal to 0, and that means that charge density is equal to 0. That's where it was when we started. And that's where it stays. In other words, this wave does not, wow, okay, fine. Small accident here. This wave does not cause any charge oscillations. This is a pure electromagnetic wave. There is a current because there is a magnetic field, but there doesn't need to be there is not charge separation. Now, from what we've seen in lecture 19, for this wave, omega square was equal to omega plasma square, but this is the omega plasma that involves both ions and electrons, plus k square c square. And in general, we can solve as we've just done for omega as a function of k, or we can wonder what my k is going to be for a given value of omega, and therefore solve for k. Then k is equal to, it's going to be equal to plus or minus 1 over c omega square minus omega plasma square. But now you see that there is something to worry about. And that is what happens if omega is smaller than omega p. Well, in that case, the quantity under square root is negative, and therefore I'm going to get the wave number to be not only complex, but purely imaginary. And what that's going to do is actually quite interesting. If I look at how my wave is going to behave, or what it's going to look like. I'll just handwrite it, or it will take me forever. Wave is going to go like e to the minus I omega t plus ik x, or whatever direction, well, z. And then since I is negative, I'm sorry, k is imaginary, I got I times I, and I got a plus or minus sign, so this is going to look like e to the plus or minus k, let me just emphasize absolute value of k times z minus I omega t. So that is an exponential dependence, it's not an oscillation. It's not quite a wave anymore. It just grows or goes to zero. Well, it can grow because of boundary conditions. Therefore, it needs to go to zero. We can only pick I can only use the root, the negative root. What is happening is that the wave will not oscillate as it travels to the region where the plasma frequency is larger than the frequency of the wave. And this type of wave is called an evanescent wave. So I will just go to zero, like e to the minus kx, k0, or ky, depending on in which direction is the direction of transmission. And the location in space where the wave turns from being oscillatory to being evanescent is called a cutoff. And no surprise here, if the cutoff is determined by a frequency, is called, that frequency is called the cutoff frequency. Let me fix this. You will also see cutoff written with a dash, and I forget what our textbook does, or written as a single word. Another way to realize or understand that there is such a thing is to take our axis and make, let's see how this looks. Okay. It's not bad. So if I put K here, I don't want an arrow, sorry, and then omega here, the frequency will look, let's see, it's something like these two are supposed to have the same angle, and they're not that bad. Okay, now when k or omega goes to infinity, let's look back up here, then I can sort of neglect omega plasma with respect to omega, and therefore my plasma frequency, my wave frequency is just going to be approximately equal to c times k. This curve is the curve omega over equals to kc. So maybe use a different color. Don't need any shapes. That's what happens up here. And then I realize when omega gets close to omega plasma, from above, k becomes smaller and smaller until it becomes 0 when omega is equal to omega plasma. And for negative signs, since I only have square quantities, I see the same mirror image of the same behavior, where what I have here is the point omega equal to omega plasma. And what I've sketched here, we also have this plot that we also have in the textbook, is a good and easy way to figure out where a wave becomes evanescent and to identify cutoffs. Because if I look at this plot, I see that for omega less than omega plasma, I can't find the value of k. Well, I can't find it in the real plane, at least. That means that my wave is not wave oscillation, may have turned into an evanescent wave. That's what happens in this case. That's typically what happens. And as I move through my plot, the point where the curve turns from giving me a value of k to not giving a value of k anymore is going to be the cutoff. Then, depending on how I'm plotting things, I may see it in terms of different quantities. So what is happening here, if I have a wave that's coming in from some region and comes and meets a plasma with plasma frequency that is higher than the frequency of the wave gets reflected. It cannot travel inside this region, therefore it just bounces back. Okay. There is a bit of discussion about the effect of conduction current and displacement current and how they can be used to understand where the cutoff is. I will just mention that if one more thing, that if the plasma frequency is very high, the wave looks like a light wave in vacuum, an electromagnetic wave in vacuum. And the reason why that's the case is that the wave is oscillating so fast that neither the ions nor the electrons in the plasma have time to react to the wave, and therefore it's, from the point of view of the wave, it is as if the plasma wasn't there, because it doesn't have, it has too much inertia to react to the wave oscillations. Okay, that's almost all I wanted to mention. I will just emphasize the expressions for group and the phase velocities. The phase velocity, when you know how to calculate them. I'm not going to do any math. I'm just going to state the result. Sorry, we're still in green. V sub p, it's the phase velocity, it's not the plasma velocity. Omega over k. And looking back up here, it's pretty easy. C over, and if you take the omega inside the square root, you get, see if I can make it look nice. One minus omega plasma square over omega square. That also tells me that the phase velocity goes to infinity when omega is close to the plasma velocity. Oops. The wave frequency gets close to the plasma frequency. Okay, frequencies, velocities. And the group one is going to be d omega dk. Again, easy. Here I have omega as a function of, sorry, k as a function of omega, but which I can square, but it's trivial to solve the equation in the opposite wave. And I'm still going to have a square root. Long story short, I just get C times 1 minus omega square over, sorry, omega plasma square over omega square. So in this case, when omega gets close to the plasma frequency, then the group velocity goes down and it goes to 0 when omega is equal to omega plasma. That means the wave is not propagating anymore. The group velocity, if the group velocity goes to 0. So that's the energy with which the energy propagation velocity, the velocity with which the energy propagates, and that goes to 0 as omega goes to omega plasma. We can now move to the longitudinal mode, and briefly talks, doesn't always work, talk a little about the longitudinal mode, and then finally we'll move to magnetized waves in a magnetized plasma. Okay, now let me remind you that k cross E is 0, k dot E is not 0. By what we've said for the making things disorderly, let me state that this is the longitudinal mode. So I'm going to put a title here. Here we are. Okay, for this mode, we have k cross C equals 0. And as I was saying, by what we discussed earlier, B is going to be 0, because that's the curl, or related to the curl of the electric field. And that's what gives me the magnetic field. So there is no magnetic field in this case. However, there is going to be a charge separation. I'm going to see electrical charge, because this means that the divergence of E is non-zero. But since the curl of E is 0, I can write E as a gradient. And our textbook prefers the minus sign. It doesn't really matter. But you see from all of these pieces that this is an electrostatic mode, by which I mean that there is no electromagnetic wave because there is no magnetic field. And indeed, we have already encountered this mode. That's pretty much our plasma oscillation. Also, the group velocity in this case is 0, because remember, the frequency was equal to the plasma frequency. So if I take the derivative of omega with respect to k, I get 0. Omega doesn't depend on k. And the phase velocity is just omega over k, or omega plasma over k. Okay, that's only true if we keep neglecting the the thermal motion of the particles. I don't know at this point how far we're going to get into that, but if we include thermal motion of the particles, we'll see that the group velocity of this wave is not 0 anymore. Let me put this in writing, and you can convince yourselves that this is indeed the plasma wave we have already discussed. Now, in the time we have left, I'm not going to talk about external sources, even though these may be quite important for some of you, but what you have to work on if you have external sources is pretty much the same equations, but they're not homogeneous anymore. You're going to have a source term, and you'll have to do the Fourier transform of the source term as well and see what happens. Let's now move to something just a little bit different. Oops, I don't want to do it this way because I can't make a straight line ever. So I need to trick the system this way. Now, we're going to set the equilibrium magnetic field to be non-zero. And that's what we're going to mean by magnetized. We're going to assume that that there is no space dependence for the magnetic field. And we're going to look at waves in a cold uniform magnetized plasma. Again, magnetized means that the equilibrium B is non-zero. Well, then, if the magnetic field is non-zero, my equation of motion for the charged particles and that make up the plasma is going to look like this: equation of motion for charges. And here I should specify, I'm going to look at the first order. Again, as we've done before, I'm going to linearize my equation, assuming there is some type of perturbation. The equilibrium is non-moving, uniform, and nothing ever changes in time or space. Now I put in a perturbation, and of course, the equation of motion is going to be simply that the mass of the particles times dV, let's call it dV sub S1, then we'll get rid of the one subscript. And I'm going to skip a step and just write this as a partial derivative. With respect to t, what happens again is that the equilibrium velocity is zero. We're still assuming that. And therefore, any term like v dot gradient of v is going to be the product of two first-order quantities, and therefore it's negligible. Okay, here we have E sub s. That's a lowercase e. and is going to multiply E1 plus what we have here is V sub S1 cross D0. That is the only first order term I can make with the ingredients I have at my disposal. In the case where there was an equilibrium velocity, then I would have a term V0 B1. But in this case, the only term where the magnetic field appears in the equation of motion is through the equilibrium magnetic field. Okay, now I'm going to do the usual thing. I'm going to put direction rather, let me do it this way. I'm going to choose the z direction to be in the direction of the magnetic field. So I'm not going to assume that B is in the z direction. I'm going to make it in the z direction. Whatever direction the magnetic field is in, I orient it through z. Then you can immediately see the z component of the momentum equation is not going to have, it's not going to see the magnetic field again, because there is not going to be any component in the z direction of the cross product V cross B. I'm going to drop the subscript 1. I'm only going to keep zeros to indicate the equilibrium quantities. And I'm going to take the Fourier transform. And this is going to be pretty simple. Okay, I'm going to have minus I omega ms v s x Fourier transform is going to be equal to E sub s times E1 so EX Fourier transform plus in the x direction I'm going to have Vy Vsy Fourier transform times B0 times, write that again. Fourier transform. And the y component is going to be pretty similar. The first piece doesn't change. The first piece is the same for all of the directions, all components. This is going to look also extremely similar. Here I have EY instead of EX, and here I'm going to have VX instead of VY. And actually, sorry, just as I was finishing to write my equation, I realized I put a minus sign. I mean, I should put a minus sign there because of the way this is supposed to look, right? Okay. When we do cross products, of course, I'm going to have opposite signs. And I lost track of which sign was which. Okay. Finally, the z components got the same left-hand side, just with vz instead of vx or vy, but on the right-hand side, we only have the electric field, because there is no contribution from the magnetic field. Okay, this becomes a little less than happy, but we'll do what we need to do. What you actually go on and do is just going to sketch things for you. We're not going to do all the math. It's pretty straightforward, and you know how to do it. So I'm going to define or utilize a definition. We have defined it in other places. We're already familiar with it. The cyclotron frequency for the species S as ES B naught divided by MS. I hope you'll definitely remember about this one. Cyclotron frequency. So that lets you simplify things a little. Also, let's see. Well, can proceed in more than one way. You always end up with the same result. But what you do here is replace the magnetic field with a cyclotron frequency. Then you go and solve for V in terms of E. So let me just write it. So that's pretty trivial. What you have to do is eliminate the velocities, and that's pretty simple. You solve the equation for Vx in terms of Vy, replace it in the y equation and get an equation for Vy, and do the same thing in the opposite direction to get an expression for Vx. So at the end, I'm just trying to decide what's the most compact way to write it. I guess we can do it like we have it in our textbook, which is that Vsx, Vsy, Vsz. Oops, what happened? Technical difficulties. These are the Fourier transforms. And they're going to be equal to Es over Ms times minus I omega over well, let me write it in detail for at least for the first time. The cyclotron frequency square minus omega square. And here I have the same thing, but with omega cyclotron for the species square. No, it's not square. We're doing dimensions over the same denominator. And then have a 0 here. This one is similar, except for a sign. It's a sign that comes out of the difference in sign between Vx and Vy in the equations of motion. Okay, I got this piece, and then I got the other piece, which is the same, I omega divided by omega cyclotron square minus omega square, and 0. And here I have 2 zeros, and I over omega. And all of this multiplies the electric field. So Ex, Ey, and Ez. Now, how do we go and make head or tails or anything of this thing? Is the same thing we've done before. So please learn the logic. The algebra is pretty straightforward. It's just cumbersome. It's not worth a lot of our time. We remember that J is the sum over S of E sub S and sub S Vs, where N sub S is again the number density, which is just going to be some N0, the equilibrium one, because Vs is first order. So let me call it NS0. If we assume that the charge of the ions is one charge, then the zeroth order density is going to be the same for ions and electrons because of quasi-neutrality. But ions may have double charge or more. And if that's the case, you're going to have a lot more electrons than you have ions, to be 2 times, 10 times as many, and therefore the densities will not be the same. And now I'm going to introduce a shortcut, or shorthand rather. It's just that is not used in the textbook. I'm going to call this, just let me use capital lambda. And if I do that, I can write the plasma current with relatively little pain. Remember, these are still and always Fourier transforms or Fourier transform quantities. Okay, so J as a vector is going to be equal to the expression I have here. So that's going to give me the sum over S of density times charge square. Already had a charge with another one. Minus 0 E sub S square. That's not nearly close enough to being straight. All right. In the denominator, I'm going to have just the mass from up there. And this all multiplies matrix minus I omega divided by omega C sound and so on. This is what I call lambda. Great. And the next term is going to be omega cyclotron sound, also multiplying lambda. And 0 still. And the next equation is pretty similar. Have a minus sign there, minus omega CS times lambda. Have a sign, or minus sign also here, minus I omega lambda, 0, and then 0, 0, and the last piece I'm not going to touch. It's going to stay. That omega looks pretty iffy. It's going to be I over omega. So and this multiplies same as in the previous line, ex, ey, z. Okay. Now, hopefully you'll recognize what we're doing here. Okay, not terribly pleasant to look at. There, better. That matrix is the conductivity tensor. And we can use that to define the electric tensor. And from there, it's going to be a little bit more work, but there are sort of standard forms for doing this. But let's pause here for a little while, and we'll pick this back up on in the next lecture. Thank you for following, and I will see you soon.